this second step of computing a winning region, because at least conceptually these other steps are rather simpler for safety specifications at least, not necessarily computationally simpler. Good. Before we turn to all the new algorithms we will learn today, let's briefly recapitulate the standard algorithm for solving safety games as introduced in one of the first lectures by Bettina, I think. For this algorithm, we will use a function which we call force E. This function force E takes as an argument a set of states A, and it also produces as a result a set of states B. However, these are not really sets of states, but these are actually formulas over our state bits, and these formulas represent sets of states. And the result that is produced by this force E function is it returns all the states from which the evil environment can enforce to reach a state of A in exactly one step. This is how this force function is defined. We can also write this using a complicated quantified formula. It's actually not so complicated to understand. Basically, we say that the evil environment can enforce to reach a state of A in one step if the evil environment manages to find some input values such that no matter what the system player does with the output values, we will always end up in a next state x prime by following our transition relation, and this next state x prime is in our set A. So it satisfies this formula A. This is how you read this formula, but this is not so important for us at the moment. Just keep in mind the informal meaning of this force function. Namely, it gives us all states from which the evil environment can enforce to reach A in one step. Similarly, we can of course also define a function force S, which gives us the set of all states from which the system can enforce to reach a state of A in one step. This is just similar, but exactly the opposite thing. So the system can enforce to reach A in one step if, no matter what the evil environment does with the inputs, we as the system can always find some value for the outputs, such that the next state, which is defined by our transition relation, satisfies the formula A, which means that we are in a state of the set A. Good. How can we now use these force functions to define an algorithm which computes the winning region for a safety game? You've seen this algorithm a couple of times already before, from several perspectives, from a mu calculus perspective, from an algorithmic perspective, from an example perspective. Here is it once more. So we start our computation of the winning region by saying the first version of the winning region is simply the set of all safe states. Then, as long as the winning region changes, we say the next winning region is the old winning region without all the states from which the evil environment can enforce that we leave our region, our winning region. This without is just and not, basically. Illustrated graphically, this looks like this. Initially, we have our winning region to be the set of all safe states. Then we compute the set of all states from which the evil environment can enforce to leave the winning region. Once we have this, we just remove this region from our winning region, and this is repeated. Again, we compute the set of all states from which the evil environment can enforce to leave the winning region, then we remove this set of states, and so on. At some point, we will end up in a situation where removing this blue area from the gray area does not change W anymore. This means that we can basically stop, because we could repeat this, but this would not change W anymore, so then we can also stop. And if there is no more state for which the evil environment can enforce that we leave the winning region, then from another perspective, this means that the good system player can enforce that the play always stays in this winning region. This is this basic algorithm for computing the winning region for safety specification, which Bettina introduced in one of the first lectures. The next thing I would like to discuss is how we could implement this algorithm using a QBF solver instead of BDDs. So with BDDs, this is very easy to implement. Let's go back one slide. All we need to do is we need some AND operations, some negations, and for this force function, what we also need is some existential and universal quantifications, and all these operations are provided by BDDs. So implementing this algorithm using BDDs is not really a challenge. We just call the corresponding functions of the BDD library to implement all these operations one after the other. For QBF solvers, the situation is not so easy because QBF solvers can only take a formula and basically say whether this formula is satisfiable or not. Still, we can use QBF solvers to implement this algorithm as it is here. In this slide, basically, I just want to convince you, yes, this is possible, but we end up with huge and complicated formulas. So don't get frightened if you see large and huge formulas in the following. It's not so important that you really understand them. I just want to convince you that it is possible but complicated. So our algorithm basically just starts by saying the first version of the Wien region is our set of all states. Now in brackets I also listed the variables the formula talks about. Actually these overlines are somehow broken, but you can imagine here an overline. Good. So this was this first line. This is easy to execute. We do not have to call any solver, actually. Also, we always enter this loop at least once. So the next operation, here is also a graphical illustration, nice. Then the next step is we compute the next value of W by saying it's the old value of W and force S of the Wien region. Also here, we did not have to call any solver, we can just write down this formula. Actually, this formula is not really in a format now that is understandable by a QBF solver, but remember that this force function is quite easily defined like this, using a lot of quantification and some conjunction with the transition relation. So if we insert this definition of force here in this formula, then we end up with this formula here. And we can also simplify it a little bit by, so we know that W0 is just P, and can insert this. And we can also move this W0 here, because remember, QBF solvers require formulas in so-called premix conjunctive normal form, which means that the quantifiers always have to be on the outermost level. But this we can easily achieve by moving this part here. And this gives us this formula here. Complicated formula, and it represents basically the next iteration of our Wien region computation. The next step is now difficult. Next, our algorithm says we need to check whether W changed from one iteration to the next iteration. So we need to somehow check whether W1 is different from W0. Of course, W1 can only be smaller than W0 because we computed W1 as W0 and something. But the question is whether it is really smaller or whether it is actually the same. So the question we need to answer here is whether this next iteration of W is actually really smaller than this one or if it is the same. This question we can now answer with a call to a QBF solver simply by asking this question here. We need to check whether for all states X we have that this implication holds that P implies W1 basically. So this formula here is just W1 from before. Now again, this is not really in premix conjunctive normal form because we would have to move this part here inside the quantifier block, but this is simple to do. And this way we can just ask a QBF solver whether W1 is really different from W0 or not. Once we have done this, we can get two possible answers. The QBF solver will say these two are actually the same, then we can stop and we have found our winning region. Or the QBF solver will say, no, they are not the same. Then this means that we have to do another iteration of our algorithm. So we have to compute W2 by applying this rule here. And when we insert the definition of force and also the definition of W1, which we have here, then we get yet another much more complicated formula. I already simplified it a lot because these two parts contains the same terms, and I also already moved all the quantifiers to the outermost level. So this is roughly the formula we would get to represent the next iteration of W. It's actually not so difficult to understand. It says we must be in a safe state, and by taking a transition we must be in the safe state also in the next state, and by taking a transition we must also be in a safe state in the next step, which is quite intuitive given the way the algorithm works. So now we already see how this game works. In the next iteration we have to check whether this formula here is different from this formula here, semantically. And for that we can again use a QBF solver and so on. It's not so important that you understand all these super tricky formulas here. The message I'm going to make here is just, yes, it is possible, we can implement all these operations of this algorithm here also with a QBF solver if we always transform all the formulas in premix conjunctive normal form, but these formulas become very complicated. Not just for us to write down, but also for the solver to solve. In each and every iteration we get one more copy of this formula here, this transition relation T, which is usually a very, very large formula. And also from iteration to iteration we get one additional quantifier alternation in our prefix, which makes the formulas much harder to solve from iteration to iteration for the solver. So how this algorithm would work in practice is the first iteration will be fast, the second one slow, the third one takes a night, and in the fourth one the solver dies. So the reason is that the formulas just grow and grow and grow from iteration to iteration. I mean, maybe the computation takes just one iteration, then this approach may be fast, but if this winning region computation takes 20 iterations, then this approach will just lead to huge formulas. Good, so this was how we could in principle implement this standard approach also with QBF solvers instead of BDDs, but this is not super efficient, most probably for most benchmarks. So next we will look at another method which uses learning to solve the same problem, but before that we will do a short break of 10 minutes. Yes?
The number of Boolean variables only grows linearly, right? But the problem are all these quantifiers.
Yes. So
for all axes and stuff.
If the formula grows, this is often not such a big problem for the solver, but these quantifier alternations make the problem really intrinsically hard, because it always has to say for each input there must exist some output, such that for each input there must exist some output, such that, and this makes it really hard for the solver, because the search tree grows basically huge. Okay, let's make a break.
Ja, mal kurz zum Essen.